For Unit 6, Objective 2, let's start with some reviewing of Objective 1. Objective 1 was simplifying radical expressions. And in Objective 1, we introduced the idea that sometimes you need the absolute value bars. In this first example, we're going to need it because we really don't know what x represents. X is a variable. So if x represented a positive number, then x cubed would be positive. But if it represented a negative number, then x cubed would be negative. Now, if we were only limiting ourselves to real numbers, then you cannot take the square root of a negative number, so we wouldn't be able to do this. But if we're opening ourselves up to imaginary numbers also, which we were in Objective 1, taking the square root of a negative number would be capable of being done. So, 18, we're just going to break down 18 to 9 and 2, make a prime factorization, a factor tree, and then the 9 is the 3 and the 3. So I'm going to write out what we know so far. We know the 3 came out. There's a pair of 3s, so one of them came out. I'm going to leave some room right here. I'm going to do the square root radical. I know a 2 stayed in. And then what about this x cubed? Well, the x cubed is nothing more than x times x times x, of which there's a pair of x's right there. So one of them gets to come out, so that's going to join right there. One of them stays in right there. But this is going to be one of those reasons why we need the absolute value bars. We really didn't know whether the x represented a positive number or a negative number, and so we need to guarantee that it actually can come out of the square root. So we put the absolute value x. Remember the EVO rule? If it's an even radical, which it was, a square root is an even radical. And when the variable comes out, if it comes out with an odd power, you need the absolute value bars. And that's exactly what happened right here. So this is the answer. Now, over here, a fifth root. So I don't even need to worry about do I need the absolute value bars or not, because it's a fifth root, it's an odd root. We just need to figure out what this is. So 96 is 48 times 2. 48 is 6 times 8. The 6 can go 3 times 2. And the 8 can go 4 times 2. And the 4 can go 2 times 2. Now I'm searching for groups of 5. I see a bunch of 2s. 1, 2, 3, 4, 5. Yep, I just found 5 2s. 1, 2, 3, 4, 5. So that means I can take out a 2. And what is left on the inside? Looks like the only thing that's left on the inside is this 3 right here. So I'm going to put 2, and I'm going to put fifth root of 3. And now I have to worry about the x to the 12th. Now, I could write all 12 x's right here, but let's do some easy division. If there are 12 x's, and I'm grouping them up into groups of 5, I'm going to get 2 groups. And it's going to take 10 of those x's to get those 2 groups. I'm going to use up 10 of those x's. So all I'm going to be left with is x squared on the inside. And that's that answer. Objective 2 is all about multiplying and dividing radical terms. Now, the basic rule is when you deal with multiplication and division of radicals, outsides work together and insides work together, but you never mix outside numbers with inside numbers. Now, once you get proficient with that, or if you've already proficient with this, you'll start seeing some shortcuts you can take. But I'm just going to assume that you're learning this for the first time, and I'm going to show you the long way of doing it. So 4 square root 6 multiplied by 5 square root 3. This way always works. It's not always the fastest, but 4 times 5 would be 20. So let's put a 20 on the outside. And 6 times 3 is 18. So now I have an 18 on the inside. So my step 1 answer is 20 square root 18. Outside times outside stays outside. Inside times inside stays inside. Now, if I can simplify, I'm going to, which I can. 18 is 9 times 2. 9 is 3 times 3. So a 3 is going to get to come out. And when that 3 comes out and joins the 20 that's already there, it gets multiplied. And so your final answer is 60 square root 2. Now, for objective 2, we are adding this condition now that everything we do now with operations, multiply, divide, add, subtract, over the real number system only, which means we're not going to worry about could this be negative, and if it is negative, we would have to use I to help us out. We're not going to do that. So a problem like this, 3 square root 2 times the square root of negative 9, we're just going to say it's an empty set, because in the real number system, this can't be done. Can't be done if limited to real numbers. Here's an example of a problem that is going to use that limited to real number system rule. You can see I'm multiplying 2 fourth root radicals. So let's go with the basic rule first. Outside times outside stays outside. So this would be 15. And then it would be the fourth root of whatever's inside. 10 times 2 is 20. C to the 8th times c to the 20th. Here'd be a good place to practice our exponent rules. C to the 8th times c to the 20th. When you're multiplying exponential terms that have the same base, you just add the exponents. So that would be c to the 28th. And this would be d to the 1st times d to the 3rd, which would be d to the 4th. So that's what I call our step 1 answer. Now we need to see if anything needs to be cleaned up. Let's start with the 20, see if we can do anything to it. We can't, because 20 just goes down to 5 times 4, and 4 goes to 2 times 2. But remember, we're dealing with fourth root, which means I need to group up 4 of something before I can bring one of them out. So 20 isn't going to get cleaned up at all. Now c to the 28th, if I had 28 c's and I grouped them up into 4, 28 divided by 4 is a nice clean number. It would be c to the 7th. And there would be no remainder. So I'd have my 15. So what have I got so far? I've got my 15. I've got my fourth root. I know the 20 stayed inside. It couldn't clean up. C to the 28th becomes c to the 7th. And now d to the 4th becomes, in the fourth root, it would simply be d. Now, we still don't quite have our final answer, because if you take back and you look at does the rule for absolute value bars come in? And if it does, where does it come in? Well, take a look at this first term right here. We know D cannot be a negative number, because if it were, I wouldn't be able to take the fourth root of it. I can't take an even root of a negative number. So I know for a fact D is limited to non-negative numbers. So I don't need my absolute value bars, because if D were negative, this would not be able to be done. But how about the C? If C were negative, taking it to the 8th power would turn it positive, and this would be able to be done. C to the 20th. If C were negative, taking it to the 20th power would be positive, and so this would be capable of being done also. So, since I had an even index of a radical, and both of those C's were capable of being fourth rooted, no matter whether they were positive or negative, and this came out as an odd, I need to put absolute value bars around the C to the 7th, but I don't need it around the D. And one more time, the reason I don't need it around the D is because of this right here. We had to assume D was non-negative, because if it were negative, this would not be able to be done. Okay, moving on to the next problem. I'm multiplying a couple of cube roots. Let's take the basic rule, outside times outside stays outside. So this is a -1 times a +7 is a -7. And then I'm going to put my cube root. A times a to the 10th is a to the 11th. B to the 2nd multiplied by b to the 6th is b to the 8th. And since I'm using a cube root, an odd index, these numbers could either be positive or negative, or these variables could either be positive or negative. It doesn't matter. Now it's time to clean up our answer. I still have -7. Now, if I had a to the 11th, how many groups of 3 am I going to get? I'm going to get 3, a cubed. And it's going to take 9 a's for that to happen. It's going to use up 9 of those a's, which means a squared stays inside. And b to the 8th, if I take 8 and divide it up into groups of 3, I'm going to get 2 groups. So that would be b squared. It's going to use up 6 of those b's to do that, so I'm left with b squared on the inside. Involve some more multiplication and division like you're going to see on your worksheet. This one's distribution. So square root 5 times square root 6, inside times inside stays inside, square root 30, minus, now square root 5 times 4, that's an inside number, that's an outside number, and so therefore they really can't really do anything with each other than get multiplied. So square root 5 times 4, or if you thought it the other way, 4 times square root 5 is just square root 5. Now, you might think this is the answer. Who knows? Let's check. 30 is 10 times 3. 10 is 5 times 2. We've prime factorized it, and we haven't found any pairs. So really, that is our answer. Square root 30 minus 4 square root 5. Okay, now let's move on to some division. The same rules apply. Outside times outside stays outside. Inside times inside stays inside. So when it comes to these fractions, I tell my students the outsides can work with each other, just like normal fraction rules. So 12 over 4 makes 3, if you think of the reducing that happens. And you can also reduce the insides. So 30 over 10 is also 3. But what you do to the outsides, stay outside, and what you do to the insides, stays inside. And then if there's any more cleanup to do, then you just clean it up. But in this case, there wouldn't be. There's your answer. Now, some of you guys might remember from previous classes about rationalizing. There's a rule that says you can't have roots on the bottom. So, since this is a square root, that means I'm looking for 2 of something in order to get one of them to come out. Well, I have a single 7 on the inside, so the problem needs another square root 7. So I'm multiplying the top by square root 7 over square root 7. And what lets me do that is the fact that square root 7 over square root 7, or anything over itself, is really the number 1. And anytime you multiply something by the number 1, you really don't change it. You might change the way it looks, but you don't change the actual value. So 1 times square root 7 is square root 7. And square root 7 times square root 7, if you do it the really long way, square root 7 times square root 7 would be square root 49. Inside times inside stays inside, but the square root of 49 is 7. So really, the whole reason we introduced another square root 7 to the problem was now we have 2 of them, and when you have 2 of them, you get to bring one of them out. And that's the answer. You can't reduce these or cancel them because that's an inside number and that's an outside number. Now, rationalizing cube roots or any higher order power root, index root, that can be a little bit tricky. So with cube root, you need to remember because of the cube root, I need 3 of something in order to get one of them to come out. Well, right now, I only have a single 5. So I need to introduce 2 more 5s in order to have a total of 3 of them. So the way I'm going to rationalize this problem is by multiplying by the cube root of 25. And where did I get that 25 from? I got it from the 2 additional 5s that I had to introduce to the problem. And the answer is now going to be 1 times cube root 25 is the cube root of 25. And the denominator is the cube root of 5 multiplied the cube root of 25. Well, there's a single 5. Here's 2 more. So I had the original one and 2 more. That makes 3 of them. And so now I get to bring one of them out. Now, this is a little bit of a different variation of that problem. And this comes in the fact that this is the cube root of 49. If you wanted to, you could think of it as a single 49. But what you really want to do is you want to think of it as 7 times 7. So there are already 2 7s in this denominator. So since we're dealing with cube roots, all I need is to introduce 1 more 7 to the problem. And now I have 3. I had 2 that were originally there. It was just disguised as the number 49, but think of it as 2 7s. Here's the additional 7 that I introduced to the problem. Now I have 3, So my top is 1 times the cube root of 7 is the cube root of 7. And my denominator is, I'm not even going to really worry about what 49 times 7 is, because I see this 49 as 2 sevens. And here's 2 sevens. Here's the new one that I introduced to the problem. Now here's 3 of them, so I get to take one of them out. For my last problem, I'm going to try to put a few rules together so you can see how things work out. I've got 4 cube root 2 divided by 2 cube root 12. Now remember, one of the rules is the outsides work together. So I can take this 4 divided by 2, and I know what the answer to that is. It's a 2. And I can take this 2, and I can divide it by 12, because the normal fraction rules say that I can reduce this. 2 over 12 is 1 over 6. So this would be 2 with a cube root of 1 up there. And remember, this 4 over 2 reduced to 2, so that 2 down there is gone. And the only thing I'm left with now is cube root 6 down here. So after I've done a little bit of reducing, this is what that problem becomes. Now, the cube root of 1 is still 1, so I really just have a 2 up there. But I'm still left with this cube root of 6 down there. So we need to rationalize this. And since it's a cube root, and since 6, it can be broken down to 2 times 3, but it's still, we need to think of this 6 as simply a single 6. So since I'm dealing in cube roots, I need a total of 3 of something in order for one of them to come out. So what I use to rationalize is the cube root of 36. That's kind of the magic number that's going to make this all work. And where did that 36 come from? It came from the fact that it's really just 2 more 6s. So what I had to do was introduce 2 more 6s to the problem. Now I have 3. And so my answer is 2 times the cube root of 36 on top is simply 2 cube root 36. But the bottom cleans up nicely because a single 6 on the inside right here and 2 more 6s disguised as the number 36, but really think of them as 2 more 6s. Now I have 3 6s, of which, since I'm dealing with cube root, I can get one of them to come out. And now I'm going to use the reduction rule one more time. This is an outside number. That's an outside number. That 6 is considered an outside number. So that would be a 1. That would be a 3. So what we end up with as our final answer is cube root 36 over 3. And that is objective 2.